see, but they don't know the magic that's flowing through me. Waveforms dancing, frequencies collide. It ain't just chatter, it's a science we write. From the crackle of static to the calls on the air, operators grooving, but do they truly care? It's more than just wires and a microphone buzz. It's the heartbeat of radio, it's what truly was. Oh, they call it a hobby, but they just don't see the science behind it. The waves that run free, but when silence breaks open, a voice cuts through gray.
I want to introduce you to amateur radio science. Before I get started, I have to confess to you that in putting this video together, I have been struggling with the overwhelming number of sciences that impact amateur radio. I could spend hours telling you about amateur radio science. The struggle centers on what sciences should be included in the discussion and their relevance to amateur radio. Because there are so many to pick from, I decided it was my choice. What I've done for the purpose of this discussion is create a diagram to act as a guide which helps demonstrate some of the areas of science which impact activities performed by operators. But first, let's look at the diagram. In creating this diagram, I focused on 9 different areas of science to demonstrate the impact of science on the hobby of amateur radio. I am going to take them in this order: atmospheric and space science, electromagnetics and physics, computer and digital science, radio frequency engineering, material science, astronomy and space communications, mathematics, acoustics and human factors, and meteorology. From each one of these areas of science, I will extract 3 specific topics to discuss and use them to support my argument that amateur radio is not just a hobby, it's science. Atmospheric science is the study of the Earth's atmosphere. The Earth's atmospheric composition, its structure, its motion, the energy, and the processes of the Earth's rotation. This includes the ionosphere, a layer of the atmosphere important to amateur radio high-frequency signals. Space science is the study of everything beyond the Earth's atmosphere. Space science explains how solar and cosmic phenomena affect space near Earth and beyond. These 2 sciences fit together hand in glove because really it's from the surface of the Earth to outer space. Ionospheric physics is the branch of atmospheric and space science that studies the ionosphere, a region of Earth's upper atmosphere, roughly between 50 kilometers and 1,000 kilometers above the surface, that is electrically charged due to solar and cosmic radiation. It plays a crucial role in radio wave propagation, satellite communication, and space weather. Ionization occurs when solar UV and X-rays knock electrons off atoms and molecules, creating ions and free electrons. Recombination reverses the process, and ions and electrons recombine, reducing ionization levels. This is more common at night. Tropospheric propagation refers to the way radio waves travel through the lowest layer of Earth's atmosphere, the troposphere, which extends from the surface up to about 8 to 15 kilometers, 5 to 9 miles, depending on latitude and weather conditions. It's one of the most important types of VHF and UHF radio wave propagation, especially for amateur radio, television, and microwave communication. Here, UHF and VHF signals benefit from temperature inversions and ducting. Ducting is a special type of tropospheric radio wave propagation where radio signals become trapped between layers of the atmosphere, or between the ground and a stable atmospheric layer, allowing them to travel far beyond the normal line of sight, sometimes hundreds or even thousands of miles. The sun constantly emits a flow of charged particles known as the solar wind, a stream of electrons, protons, and ions moving at hundreds of kilometers per second. Space weather refers to the changing conditions in space near Earth, primarily caused by the sun's activity, such as solar flares, coronal mass ejections, CMEs, and high-speed solar wind streams that interact with Earth's magnetic field and upper atmosphere. Just as terrestrial weather affects airplanes and radio waves on Earth, space weather affects satellites, GPS, power grids, and amateur radio communication. Electromagnetics and physics form the scientific foundation of all radio communication, including amateur ham radio. Every signal you transmit or receive is governed by the laws of physics and described mathematically by electromagnetic theory. Electromagnetics is the branch of physics that studies electric and magnetic fields and how they interact. It explains how radio waves, which are electromagnetic waves, are generated, transmitted, and received. Electromagnetic wave propagation is the process by which radio waves travel or move through space, the atmosphere, or other mediums after being transmitted by an antenna. It is one of the most fundamental concepts in amateur radio, because understanding how waves travel and what affects them determines how far, how clearly, and by what path a signal will reach another station. Resonance is when an electrical circuit or antenna naturally vibrates at a specific frequency where energy flows easily and efficiently. Impedance is when the total opposition, resistance, a circuit gives to the flow of alternating current AC, including both pure resistance and reactance from capacitors or coils. Now don't be scared, the concept sounds difficult, but in practice it is easy. Wave polarization describes the direction in which the electric field of a radio wave vibrates as the wave travels through space. Polarization is the orientation of the radio wave's electric field, usually horizontal, vertical, or circular. For the strongest signal, transmitting and receiving antennas must have the same polarization. A vertical antenna works best with another vertical, a horizontal with another horizontal. Mismatched polarization can cause signal loss. Circular polarization helps maintain contact even when antenna orientation changes, like with satellites. Computers and digital science play a major and growing role in amateur radio, transforming it from simple voice and Morse code transmissions into a world of digital communication, automation, and signal processing. Digital science in amateur radio means using computers, software, and digital signals to send, receive, and process information, instead of relying only on analog voice, or CW, Morse code. Computers handle the encoding, decoding, logging, and analysis of signals, making radio communication faster, clearer, and more reliable. Digital signal processing, DSP, in amateur radio means using computer or microprocessor technology to analyze, modify, and improve radio signals after they have been converted from analog, electrical waves into digital form, numbers. In simple terms, DSP is a computer working on your signal to make it clearer, cleaner, and easier to hear or decode. A simple way of saying that is digital signal processing, DSP, is the use of math and computer algorithms to filter, shape, or enhance signals that have been changed from electrical waves into digital data. Modulation means changing, modifying, a radio wave so it can carry information, such as your voice, Morse code, or digital data. The radio wave itself is called a carrier wave, and modulation puts your information on that carrier. When you speak into a microphone, your voice creates an audio signal. The transmitter mixes that signal with a radio frequency, RF carrier wave, producing a new signal that carries your voice through the air. Coding in amateur radio means turning information into a set of symbols, tones, or digital bits so that it can be transmitted and then correctly decoded at the other end. In older systems, coding could mean Morse code, a simple form of digital communication, dots and dashes. In modern systems, it means digital data encoding used in computer-based radio modes. Networking means linking radios and computers together so that information like messages, data, or even internet connections can be shared between stations. In the digital age, amateur radio operators use radio-to-computer and radio-to-radio networks to send text, images, files, emails, and telemetry around the world, even when the internet is down. In traditional radio, each contact is one-to-one. you and another operator. With digital networking, computers create a system where radios act as network nodes, points that pass information. Digital signals carry data packets between stations. Software manages routing, error correction, and storage, like the Internet does. This allows store and forward messaging, automatic relays, and worldwide connectivity through linked systems. Radio frequency RF engineering in amateur radio is the science and practice of designing, building, and understanding systems that use radio waves to send and receive signals. It focuses on how electrical energy becomes radio energy, how that energy moves through the air, and how it's received and turned back into useful information. Radio frequency engineering is also the study and application of electromagnetic waves, radio signals, used in communication, including transmitters, receivers, antennas, feed lines, and filters, to make sure signals travel efficiently and clearly. Antenna theory is the study of how antennas transmit and receive radio waves, how electrical signals are turned into electromagnetic waves, and how those waves travel through space. Antenna design is the practical process of creating antennas that work efficiently at specific frequencies and for specific purposes, like long-distance, local, directional, or satellite communication. In amateur radio, transmission lines, also called feed lines, are just as essential as the radio and antenna themselves. They are the scientific and physical link that allows radio frequency RF energy to move efficiently from your transmitter to your antenna and from your antenna back to your receiver. The transmission line carries the RF energy from your radio to the antenna with minimal loss. If your feed line is poorly chosen or mismatched, much of your transmitter's power never reaches the antenna. It's wasted as heat. Every part of a radio system has an impedance, usually 50 ohms. If the transmission line's impedance doesn't match the transmitter and antenna, some of the signal reflects back toward the transmitter. This reflection creates standing waves, measured by the SWR, standing wave ratio. A filter is an electrical circuit that allows certain frequencies to pass while blocking or reducing others. In other words, filters shape and clean radio signals so you can transmit and receive only what you want, and not the noise or interference nearby. Filters rely on the behavior of inductors and capacitors. These components store and release energy in magnetic and electric fields, and at certain frequencies they either resist signal flow or let signals pass easily. An antenna tuner, also called a matching network, is a device that adjusts the impedance between your transmitter, feed line, and antenna so that maximum power is transferred. The tuner does not actually tune the antenna itself. It matches the system so the radio sees the correct impedance, usually 50 ohms. Material science is the study of how the structure and composition of materials affect their physical and electrical properties, like conductivity, resistance, magnetism, heat tolerance, and corrosion resistance. Every piece of equipment, antennas, feed lines, power supplies, connectors, circuit boards, is built from materials whose electrical, magnetic, and mechanical properties determine how well they perform at radio frequencies. Understanding materials helps amateur radio operators and designers choose the right metals, insulators, and components so that signals move efficiently, equipment lasts longer, and energy losses are minimized. A conductor is a material that allows electric current and radio frequency RF energy to flow easily through it. Conductors have very low electrical resistance, meaning electrons can move freely. They are used anywhere you want electricity or radio signals to travel, such as in antennas, feed lines, connectors, and radio circuits. An insulator is a material that does not allow electric current to flow easily. It has very high resistance. Insulators are used to support, protect, and isolate conductors so that electricity and RF energy stay where they're supposed to and don't leak or short out. A dielectric material is a non-conductive substance, an insulator, that can store electrical energy in an electric field when exposed to voltage. A dielectric is a special kind of insulator that doesn't let electricity flow, but does respond to electric fields, making it essential for handling radio signals efficiently. In amateur radio, dielectric materials are used anywhere electricity and radio frequency, RF energy, need to be controlled, separated, or stored, such as in coaxial cables, capacitors, antennas, and circuit boards. Thermal management in amateur radio means controlling and removing heat from radio equipment so it can operate safely, efficiently, and reliably. Whenever electricity flows through components, especially transmitters, amplifiers, power supplies, or voltage regulators, some of that energy becomes heat. If that heat is not properly managed, parts can overheat, fail, or change performance. This can cause frequency drift and distortion. Astronomy and space communications in amateur radio refer to how radio waves are used to study space phenomena and communicate beyond Earth's atmosphere, including satellites, the International Space Station ISS, and even the Moon. So every space communication contact is both a practical radio operation and a real-world physics experiment. Earth-Moon Earth, EME, also called moon bounce, is a method of radio communication where signals are sent from Earth, reflected off the Moon's surface, and received back on Earth by another station. Let's talk the science behind it. The distance to the Moon is about 239,000 miles, so the round trip for the signal is roughly 480,000 miles. The total delay between transmission and reception is about 2.5 seconds. The Moon reflects only about 7% of the signal. The rest is scattered or absorbed. Because the reflected signal is so weak, EME requires very sensitive receivers, low-noise amplifiers, and often digital weak signal modes. Satellite communication is the use of radio waves to send signals between Earth and artificial satellites in orbit, and then back down to other points on Earth. In amateur radio, satellites act like repeaters in space. The satellite receives a signal from one amateur station on Earth, the uplink. The satellite transmits the signal back down to another station, the downlink. This allows operators to communicate across hundreds or even thousands of miles, beyond the normal line of sight of terrestrial radios. Deep space communication in amateur radio refers to the study and practical use of radio signals that travel beyond Earth's immediate environment, to the Moon, planets, asteroids, or deep space probes. It combines amateur radio technology, astrophysics, and radio astronomy to explore the farthest limits of communication. Mathematics in amateur radio is the use of numbers, formulas, and calculations to understand and design how radio signals behave, including frequency, wavelength, power, resonance, impedance, and propagation. Mathematics is the language that explains how and why amateur radio works. It's behind every antenna you build, every signal you send, and every contact you make. Without math, we could not design transmitters, tune antennas, or understand how radio waves travel through space. A logarithm is a mathematical way to express ratios or changes in size, especially when values cover a very wide range. In radio science, signal powers can vary from a few watts to trillionths of a watt, so logarithms make these huge ranges easier to manage. Trigonometry in amateur radio is the math of angles, direction, and wave motion. It helps operators aim antennas, predict propagation, design arrays, and understand how radio waves travel and reflect, turning geometry into clear, strong signals. Radio waves themselves are sine waves, and all modulation, AM, FM, digital, is built on trigonometric waveforms. Statistics deals with collecting, analyzing, and interpreting data, while probability measures the likelihood of an event happening. In amateur radio, these two branches of math help operators and engineers understand unpredictable behavior, like noise, fading, interference, and signal errors. This aids in designing systems that work reliably, even when conditions vary. While most people think of amateur radio as electronics and antennas, statistics and probability are also quietly at work behind nearly every radio signal, especially in signal analysis, noise reduction, digital communication, and propagation prediction. Acoustics is the science of sound, how it is produced, transmitted, and heard. In amateur radio, acoustics deals with the quality of the audio signal, how voice, tones, or Morse code are generated, transmitted, and reproduced through microphones, speakers, and headphones. Acoustics in amateur radio is about how sound energy, your voice, tones, or CW beeps, becomes electrical energy that travels by radio waves, and how it is heard clearly and comfortably on the receiving end. Human factor refers to the human element in the design and operation of radio systems, including hearing, speech, reaction time, ergonomics, fatigue, and perception. It's the study of how people interact with technology, especially under stress, long hours, or weak signal conditions. The human factor in amateur radio is also about how the operator's senses, reflexes, and decisions affect the quality and success of communication. Audio processing in amateur radio is the electronic manipulation and control of sound signals, usually your voice, to improve clarity, intelligibility, consistency, and loudness before transmitting or after receiving. Audio processing is how a radio polishes your voice so it sounds clear, strong, and easy to understand, even under noisy or weak conditions. Psychoacoustics is the science of how humans perceive sound, how your ears, brain, and emotions interpret audio signals, not just how the physics of sound works. It combines acoustics, sound waves, psychology, perception, and neuroscience, hearing process. Psychoacoustics is about how your brain hears and understands what your radio produces, not just what the equipment transmits. Ergonomics may sound like a comfort topic, but in amateur radio, it's deeply tied to operator efficiency, safety, and performance, especially during long operating sessions, contests, or emergency communications. Ergonomics is the science of designing equipment, workspaces, and systems to fit the human body and mind, instead of forcing people to adapt to the equipment. It studies how people physically and mentally interact with technology, with the goal of improving comfort, accuracy, efficiency, and safety. Meteorology is the scientific study of the atmosphere, including weather patterns, temperature, humidity, pressure, wind, and precipitation. In the context of amateur radio, meteorology plays a vital role in understanding how atmospheric conditions affect radio wave propagation, signal strength, and communication reliability across various frequency bands. The Earth's atmosphere is a multi-layered envelope of gases that surrounds the planet. The atmosphere is divided into distinct layers, each with unique temperature patterns, density, and ionization properties that influence radio communication. Its structure and composition determine how radio waves behave as they travel from transmitters to receivers. In amateur radio, understanding these layers is essential for predicting propagation, signal range, and clarity across different frequency bands. Tropospheric refraction is the gradual bending of radio waves as they pass through layers of the troposphere that vary in temperature, pressure, and moisture content. Because air density decreases with altitude, the refractive index of the atmosphere also changes, causing radio signals to curve slightly downward toward the Earth instead of traveling in a straight line. Tropospheric ducting occurs when temperature and humidity create a temperature inversion, a layer of warm, dry air sitting above cooler, moist air near the ground or over the ocean. This forms a radio duct or waveguide that traps VHF and UHF signals between two layers of the atmosphere, or between the Earth and the inversion layer, allowing them to travel hundreds or even thousands of miles. System design is the process of planning, assembling, and interconnecting all components of an amateur radio station so that they function as an integrated, efficient system. It includes transmitter and receiver selection, antenna design, grounding, cabling, power supply, and station layout. Safety in amateur radio involves all practices that protect the operator, the equipment, and others from electrical shock, fire, radiation exposure, mechanical injury, or environmental damage. With the completion of the section on meteorology, we have covered all 9 areas I outlined at the beginning of this video. As you can see, Amateur radio was born of science, and science continues to be the driving force for innovation and change. As I conclude this video, I would like to share my feelings that I do not want anyone to view this video and decide amateur radio sounds too scary. The science is built into the education and testing curriculum. The path is already there. You just need to follow it. If a 12-year-old can do it, so can you. Amateur radio is a hobby with science baked in. We tell all our students that amateur radio is not rocket science, just a whole lot more fun. And we mean a whole lot more fun. So I'm going to finish this out by letting you listen to the rest of the song, Ham Radio Blues.
The science behind it, the waves that run free. When silence breaks open, a voice cuts through gray. Ham radio magic, come join in the play. Turning dials in the dark, under the moon's light. Every call I make is a spark in the night. But sometimes I wonder if we truly understand the power of science in the palm of our hand. It's the whisper of waves, a crest in the tide. In this ocean of signals we swim and we ride. From Morse code to digital, each tone has a tale. But do we feel the force that powers our sail? Oh, they call it a hobby, but they just don't see the science behind it. The waves that run free. When silence breaks open, a voice cuts through gray. Ham radio magic, come join in the play. So if you wanna play with science, take a chance. Grab that mic, tune your heart, join the dance. With antennas soaring, we connect the skies. In the chaos of signals, let your spirit rise. From the hum of the gear to the thrill of it all, it's a raw, playful journey, just